So in this video, we're going to solve some problems involving the derivative of exponential functions. So before we start some problems, let's actually review derivatives of exponential functions. So let's start off with y is equals to, for example, 5 to the power of x. We'll keep it simple. So the derivative from the previous video is exponential is itself, but then there is a stretch factor or vertical compression factor. It's going to be ln of 5, the natural log. Over here we have e to the x, and e to the x is one of the rare functions where the derivative is exactly itself, where there is no stretch factor or compression factor. It's a 1, which is the same thing as itself. And again, let's review what happens if you have a function within the exponential function, a composite function. Let's actually put sine x. Let's actually be more like adventurous. So to do this, the derivative, look at the bigger function. It is e to the sine x, so it is itself. The stretch factor is a 1 because if you take ln e, it's the same thing as 1. So over here, and the next thing we have to do is find the derivative of the inner function, which is going to be sine. So the derivative of sine x is cos x. So in this first problem, we're going to look for the potential turning points, right? So turning points are where the slopes of the function is 0. So for example, here's a turning point. The tangent, the slope of the tangent here is flat, 0, or could be this way. All right. When I say potential, we haven't really learned how to confirm whether something is a turning point or not a turning point. But well, that's why I call it potential. So to do this, we're going to find the slope where the derivative is 0. So we take y prime and we set it to 0. Let's actually find the derivative of this function here. Now this function is a product. You got an x and you got an ex. So we're going to do the product rule. So product rule says the following. Let's find the derivative of the left, keep the right, plus the derivative of the other piece. So this little sign means prime, and then we keep the x. So the derivative of x is just 1. I'll just leave it as that. Now the derivative of this function is itself, so it's just ex. And this one here, I'll put a bracket x, right? So now we want to set this to equal to 0 because we're solving for the x points on the function where the slope is 0. So in this case, how do we solve for exponential function? Now in this case, when you solve for zeros, ideally you would like to have things in factored form. In this case, we have two terms or two parts to this. In this case, they both have e to the x, so let's factor e to the x out, and we're left with 1 plus x, which gives us equals to 0. So this is factor form. Then we can solve. We set each piece to equal to 0. 1 plus x equals to 0. X is equals to negative 1. And this one here, well, keep in mind, this e is 2.718, and this x is a number. When the base is positive, whatever input number that you put in here will also be a positive. You can do this graphically. So if you graph this function, it's exponential. It's increasing because the base is 2.718. And we know that this exponential function is always above the x-axis. It's never below. It doesn't even touch the x-axis. Or if you don't want to take it from a graphical point of view, you can actually, if you wanted to do, you can ln both sides or log both sides. In this case, I can change this to a log form if you really wanted to. So log exponential form to a log form, that becomes base e and 0. And if you put this in your calculator, or you can change this to ln 0, because log e is the same thing as ln 0, you're going to get an error. That number doesn't exist. Now, so that means we only have one point, a potential turning point, and in this case, it's asking for points. So that means you need to solve for the y value, the coordinate. So to do this, you're going to take the x, -1, and substitute it back into which function? The derivative or the actual function? In this case, we're going to sub it back into the original function. If we sub -1 back in, we're going to get 0, which we don't want. So we're going to actually sub in -1 back into the original function, e to the -1, and then we're just going to simplify this. We go to negative reciprocals. It's the same thing as 1 over e, and then that becomes -1 over e, and therefore -1 and -1 over e is a potential turning point. So in the future lessons, we're going to learn how do you verify that something is a turning point. In example 2, we're going to actually work with a exponential function. This actually should be a bigger bracket where the base is not an e. So in this case, we have a function, an exponential function, and you want it to be parallel to 6x plus 5, so linear function. So imagine this graph, and imagine a linear, 6x plus 5, you pretty much want to figure out where on this graph is the tangent, the slope of the tangent, the same thing as the slope of the line here. The slope of the line here is 6, so m is equals to 6. So to find this part here, you're going to have to find the derivative. Again, you want to find the slope of the function and set that to equal to 6. But first, the second part is we need to find the derivative of the exponential function. In this case, 3 and 2. Now, just a note, please don't multiply 3 times 2. Okay, that is not a proper algebraic method. Because in BEDMAS you do this first and then you deal with 3. So we're not going to multiply 3 times 2. So to find the derivative of a constant multiplied by a function, that constant you just leave it outside. Then you actually focus on the derivative of the exponential function, which is in itself the same thing, 2 over 4x. And then you want to figure out the stretch factor or the whatever factor you want to call it, ln 2, but you're not done yet because this is a composite function. There is a 4x within the exponential, so you got to take the derivative of this. So we're going to clean this up a bit. We're going to take all the constants together. So 3 times 4 is 12, so 12 ln 2. All right, I'll just put a bracket around here, and then just to separate it from the exponential part. All right, and you want that to equal to 6 because this is the slope of the tangent and this is the slope of the line. Now, how to solve for this? We're going to have to isolate for x. So meaning we're going to have to divide everything by this constant here. So 2, or coefficient, and that equals to 6 over 12 ln 2. And that becomes 4x. So we're going to reduce the 6 over 12, which is the same thing as 1 over 2 ln 2. And now we're going to have to solve for this. Is that right? We're going to have to solve for this. Yes, so this is exponential form, base, exponent, and this part here. We can change into log form or ln form. I'm going to change it to a log form. So log base of 2 and this fraction to the right. And then at the end, you have to divide everything by 4. Divide everything by 4. So x is equals to log 2 bracket 1 over 2 ln 2 all divided by 4, and then you get some sort of number. So this last example is asking for the slope of the normal. Just to recap, the normal is a line that is perpendicular to the tangent. So meaning that the slope is of the normal is a negative reciprocal to the slope of the function at a specific point. So we're interested at this point here, x is 0. So what we're going to do right now is let's find the slope of the tangent at this point here. But first we need to find the derivative. In this case, we're going to use bigger pictures, the quotient rule. So just to write this out, the quotient rule says find the derivative of the numerator. So I'll put here the derivative sign, then you multiply by the denominator minus the derivative of the denominator multiplied by 2x all over ex to the power of 2. So now we can work out the derivative. Now the derivative of this piece here is itself, but don't forget there's a ln 2. This is not a composite function, it's just an x. We don't have to worry about this. Then we bring down the ex minus derivative of this piece is itself with no stretch factor, and then we have this piece as is 2x all over e, and I'm going to just use the exponent law and multiply these two together. So this is our derivative. We don't have to simplify anything because at the end we're going to substitute the 0 in. So we sub in 0 anywhere. So we have ln 2. Now we know that I'm not going to sub it in right now, but 2 to the power of 0 is going to be 1. So I'll just put a 1 here. 1 minus 1, 1 all over 1. All right, at the end we end up getting what? Ln minus 1. So that's it. So this is the slope of the tangent, but we want to find the slope of the normal. So to do that, all we do is take the negative reciprocal of this value here. There should be a ln 2. All right, so in this case, you take the reciprocal of this. That becomes 1, negative 1 all over ln 2 minus 1.